Assalamu alaikum students. Today we have to start our lecture number 4. In lecture number 4 we have to look today on a numerical example of sending a data file over a circuit switched network. Okay. How long it will take to send a file of 640,000 bits from host A to host B over a circuit switched network. So let's start with the calculation of this example. You have two hosts here, host A and host B. Host A and host B. Two computers are there. The link is circuit switched network, and on this circuit switched network we are going to use time division multiplexing, TDM. So we are going to use here TDM technique, time division multiplexing, and with the help of time division multiplexing, it means the link will be divided into different time slots. So all the links are carrying equal data rate, which will be 1.536 megabits per second. It is a circuit switched network. Circuit switched link, and the technique is we are using TDM, time division multiplexing, and the bit rate is 1.5 36 megabits per second. Each link will use TDM with 24 time slots. Okay, so TDM will be 24 time slots per second. And now what the connection establishment time, 500 milliseconds are required to establish an end-to-end circuit. So connection establishment time is 500 millisecond. Okay, let's work it out how we can calculate the time, that in how much time the file size is 640,000 bits. How long it will take a file of this size to send it on a TDM link having 1.536 megabits per second data rate. How long it will take to transmit a file from host A to host B. Okay, so first you have to calculate the data rate over each TDM time slots, because each time all the links are 1.536 megabits per second. As you know that what will be the data rate for each circuit, okay, because it is a circuit switched network, so each circuit data rate should be calculated. So each circuit will have a transmission rate of 1.536 into 1000 divided by 24 time slots are there. Okay, why we multiplied it with 1000? Because it is in megabits per second. Okay, and we have to convert it into kilobits per second, so it will be 64 kilobits per second. Clear? Now you have to look into it that we know that we have to look into it that how long it will take, the time. In order to calculate the time, we studied the formula in the last lecture. The delay it will take will be equivalent to L upon R, the size of the file, the number of bits divided by the data rate. So what is the size of the file? 640,000 bits. Do remember it is in bits. Okay, you have to divide with the data rate, and data rate here is in kilobits. So you have to convert it into bits. So you have to multiply it with 1000. So it will become 64,000. Clear? So how much it will be? 10 seconds. Is it clear? 10 seconds. But here it is mentioned that 500 milliseconds are required to establish an end-to-end circuit. So you have to add into these 10 seconds 500 milliseconds. So these are 10 seconds. This time is in milliseconds. So you have to convert it into seconds, from milliseconds to seconds. So 500 milliseconds mean how many seconds? 0.5 seconds. So total time will be 10 plus 0.5. Total time is equal to this time, file transfer time, plus circuit establishment time. So it will become 10 plus 500 millisecond will be 0.5 second is equal to 10.5 seconds. So this is the answer. So it will take 10.5 seconds to transmit a file from host A to host B over a circuit switched network in which we are using TDM technique with 24 time slots per second, and the link is of data rate 1.536 megabits per second, and it needs 500 milliseconds to establish an end-to-end circuit between host A and host B. Is it clear, guys? Yeah.
There's one time between send the file from the A to B.
You don't consider it delay, you consider it time. Okay, how much time it will take?
About the second.
Second, which one? Here or this one?
64 kilobits.
64, because the link data rate is 1.536 megabits per second. First you convert it into, you have to check the, because there are 24 time slots in 1 second. So you have to convert this data rate, okay, for the 24 time slots. Each time slot you have to check. Each circuit transmission rate you have to check. Okay, so you have to divide it with 24 time slots. Clear? To get the transmission rate for every time slot, 64 kilobits per second will be taken by every time slot. So the size of the file is 640,000 bits. So how many time slots will carry this data? Definitely multiple time slots will carry this file, and how much time those time slots will take, this is the total of that. This will be the time, and this is the circuit establishment time. This is the time to transfer the file, and this is the time to establish a circuit. Because as it is a circuit switched network, the technique used on the network is circuit switched network. So first you have to establish a circuit between the two hosts, then you will be in a position to transmit the file. So definitely the circuit establishment will take some time, and then you will start transferring the file. Without establishing the circuit, you can't transmit the file. This is the requirement of the circuit switching technique. Clear? Network core. What is on the network core we are using on the, when we talk about internet is a packet switched network, and it uses packet switching technique. Telephone network, as we studied, it uses circuit switching technique. In order to switch the data from one host to another host, it will establish the circuit, and then it will start switching the data over the predefined circuit which is established, and that circuit will remain reserved for the duration of the call in between the two parties, for the two parties, and the two parties will keep on exchanging the data on that pre-established circuit. And even if the parties are not transmitting the data on that pre-established circuit, it will be kept reserved for those two parties, even if the circuit is not being used by the two parties. So it is a wastage of a bandwidth. This is the drawback of circuit switching. Rather, this time can be used for some other host to transmit the data if the circuit is being shared among the other users. The bandwidth is a very costly resource which should not be wasted. So this is the beauty of the internet and the technique which is being implemented over the internet packet switching network, that if a circuit is being used between two routers and nobody is transmitting, two parties are not transmitting on that circuit, some other user can, or some other host can utilize that circuit's bandwidth, because bandwidth is a shared resource. The first thing on the internet, the resources are being shared, and the bandwidth is one of the resources. It is also being shared among different users. So bandwidth is not kept reserved as like the circuit switch network. So it can be utilized by the other users. So whoever needs to share that resource, which is bandwidth, of course, can be utilized or can be shared by the number of users over the internet. As you know, multiple users are using the internet. So internet, on the network core we have packet switching on the internet, and each end-to-end data stream is divided over the internet into packets, small chunks. These chunks are called packets. Okay. On the transport layer we call them segments, on the network layer we call them packets, and on the data link layer we call them frames. We will look into the details of these protocol data units, PDUs, on different layers, and we will look into their headers and what type of information will be contained in the headers. For example, the addresses on the transport layer segment header, source port, destination port, and the addresses in the packet header on the network layer will be the source IP and the destination IP, and the addresses in the header of a frame on the network layer will be source MAC and destination MAC address. Clear? As we will proceed further in this course, we will look into these details, and with the passage of time it will be very clear to you that what we are using on which layer, what type of PDUs we are using, and what type of addresses are there with which we have to deal. Okay. User A, B, packet share network resources. So users are A and B, and they are going to use the packets, and they are going to use or share the network resources. Okay. So for user A and B, each packet will use the full capacity of the link, full bandwidth, because bandwidth is not going to be divided. Okay. Resources are used as they are needed by the users, and their packets are transmitted over the resources. Here, bandwidth division into pieces is not performed like time slots in circuit switch network. And here you are not going to dedicate the resources. You are not going to allocate it. It is not a dedicated allocation of the bandwidth or of the router to two users. No. And resources reservation is not being performed here anymore on the packet switching network. as it was done on the circuit switching network. We have to reserve the bandwidth, we have to dedicate the resources, and we have to reserve the resources. So definitely, if multiple users will be competing for the resources, there are chances that there will be contention for the resources, on the resources. So the overall demand for the resources can exceed as compared to the amount available of the resources, because multiple users will compete to get the resources, to share the resources. As we told, that resources are being shared, even the link, router, switches, these all are the resources which will be shared over the internet, as internet is a packet switch network. If the resources are shared, so it means multiple users will be competing to get share of those resources. When they are competing to get the share of these resources, there will be a time will come when there could be contention for the resources, when the multiple users will be contending for accessing the resources. So at that time, it might be possible that due to multiple hosts who are competing to get the resources, a situation will come up when congestion starts developing over there. So packets needs to be stored on some place, otherwise the packets which are coming from the input ports, and if more hosts are sending packet towards an intermediate device, and the device will not have some sort of queue in order to store the packet, okay, so the packet will start dropping on the input queue, on the input port, because definitely a router, when multiple hosts are sending packets towards an intermediate device, for example a router or a switch, and the switch or a router has to process those packets in order to switch them to the proper network, the router will take definitely some time, because when the router will receive a packet, it will look into the header of the packet in order to determine the destination network address. So it will look into the header of the IP packet and take the destination network IP address and compare it in its routing table, because every router will have a routing table, and it will compare whether that particular router can route a packet to the appropriate destination or not. So it will have a comparison of the destination IP address in the header of the IP packet with its available network in the routing table. If it finds a match, it means it can route the packet to that appropriate network, to that destination network. And if it will not find a match, it can't route to that appropriate network, but definitely we should have another solution than where it will send the packet. What it will do with the packet if it will not find the proper match in its routing table? What it will do with that packet? Will it drop the packet or get it back, send it back to the source? No. Yes? It will keep on revolving on the internet, wandering on the internet. Isn't it? No. Anyone else? Every router should have a default route, because it is not possible for a router to have all the destination addresses in its routing table. Otherwise, if he will have all the destination networks in its routing table in the world, the size of the routing table will become huge. So in order to keep them smaller, it is not possible to have all the destination network addresses in the routing table. What it will do, it will have a default route. So default route means if it will not find a match for the proper destination network, it will send the packet to its next immediate hop or the default route, so that the next router will take care of it and it will repeat the same process. It will try to look into its routing table. If it will find a match, if it finds a match, it will route it to the appropriate network. It will send it out on the appropriate destination port, which could help in order to deliver the packet to appropriate network. Otherwise, it will also send it to the default route. So every router will have a default route in case if it does not find a match, proper match for the destination network, it will forward it to the next network, so that the next router will can take care of it. So congestion, this why I mentioned this thing here, because this comparison will take definitely some time. So it will not be possible for the router that as a packet comes to the router, immediately it processes it. Definitely this processing will take some time. So for that time, the router has to store packets in at some temporary location. That temporary location is called a queue or a buffer. So every input port will have a buffer where the incoming packets will be stored for time being, unless until the router will keep on processing the packets which are already there at the head of the queue, will take the packets from the head of the queue, process them, and go through this process and send them on the appropriate output link so that they can be reached towards their destination. Definitely a situation can arise when congestion will start developing on the router, and the router will be in a position when there will be more traffic on the router and it will congest the network. So definitely, in order to handle the congestion, router should have the packet queues in order to temporarily store the buffer, and we will study other congestion control techniques as well in this course when we proceed further, that how to handle the congestion over the network. And in that queue, the packet will wait for the link. On the link, the packet will wait in order to be processed on their turn. Okay. Store and forward method, the switch will or the router will work on a store and forward strategy, that the packet will be stored in the buffer and they will be taken from the buffer and they will be forwarded to the appropriate port in order towards their destination. So packets will move one hop at a time, because if you want to send a message, from example, from here to Google, if you want to browse the Google web page, it is not possible for you to directly connect your computer with the Google. Definitely on the internet you will be connected with the Google through going through number of hops. Okay, so it will be an indirect connection in terms of if you talk about on the internet. So your packet or your request will keep on going through multiple hops in order to reach it to the destination when you start it when you send it from the source computer. Okay, so it will move at a time and it will keep on crossing every hop, and every hop will repeat the same process as we discussed right now. So not receive complete packet before forwarding it. Every node will receive the complete packet and repeat this process and then forward it to from appropriate output port towards its destination. This is the process. This is the router over here. This is the buffer in the router. The packets are coming from host A and host B. We discussed in our example two hosts, host A and B, which will be sending the packets, and it is 100 megabits per second Ethernet LAN link, and this is the LAN port of the router. The packets will come on the router and they will be put into queue of packets, and they will be waiting for their turn to be processed and to be transported or sent out on the output port, output link. Okay, so every packet will be entering into the queue from the tail, and it will be taken out and it for the processing from the head. And this is 1.5 megabits per second link, and it is on that link we are using TDM technique, but an enhanced version of the TTM, which is called a statistical time division multiplexing. We are using that. What is a statistical time division multiplexing, STDM? That packets are switched on this link, but the time slot which is not being utilized by a particular user, if he is not transmitting in its particular time slot, that slot can be used by the other user other host instead of wasting that time slot. Okay, so we can have a better utilization of the link with STDM as compared to simple TDM. Yes. Statistical multiplexing, time division multiplexing. In the simple time division multiplexing, which we studied in our last lecture, every host will be given a time slot to transmit its packet. Okay, if in that time slot a particular host is not transmitting its packet, that time slot will be wasted. Rather, it could be used by another host. If we are wasting that time slot, it means we are wasting the bandwidth for that particular time slot. Why don't we use that time slot for some other host to transmit the data? This is called statistical multiplexing, time division multiplexing. So on this link, by using a statistical time division multiplexing, the packets will be transferred or transmitted to the next hop, which will be a next router, and ultimately they will reach to their destination C, D or E. Now you can look here that if A wants to send a packet to, for example, E, it will cross hop 1, hop 2 and hop 3. So how many routers the packet will cross or jump in order to reach to the destination from source A to source E? 3 routers. So there are 3 hops in between source A and host and destination E. Clear? So this is that the routers will be in between, called the hops, and the packets which starts its journey from the source host A, in order to reach till its destination host E, it has to go through 3 different routers, and every router will repeat the same process. So sequence of A and B packets does not have a fixed pattern. Bandwidth is shared on demand. Whatever bandwidth is required, that will be shared on demand, and it will be statistical multiplexing. TDM, each host gets same slot in revolving in turn in the TDM frame, whereas in a statistical multiplexing, it is not necessary that you will get the same time slot on your turn. If you are not transmitting, your turn can be given to someone else, and in order to save the bandwidth, the packet of the other host can be sent in that time slot. Clear? Yeah, actually it will be a better utilization of the link in order to save the bandwidth of the, because bandwidth, as I told you, it is a very costly resource. We can't afford it being unutilized. We have to utilize it. Clear? So packet switching, as I told you, works on a store and forward strategy. So the source host will send a file of L bits to router, first router, and the link is having a data rate of R. Okay, so it will take L upon R seconds or time to transmit a file of size L being transmitted over a data rate of R, and it will take this much seconds to be transmitted or to push out packets of L bits length on a link of R bits per second data rate link. Clear? The same formula we used in our numerical, L upon R. Okay. Store and forward, entire packet must arrive at the router before it can be transmitted, as we discussed already on the next link. And delay, how much delay it will take now. First I have written here delay, then I change it to time. Now if it is a point-to-point link, you can call it delay, but in case of 3 links, you have to get the you have to calculate the accumulated delay, because your packet, in order to start its journey from source and in order to finish its journey on the destination, it has to go through 3 different links, 1, 2, 3, and all the 3 different links can have different data rates. Okay, so delay will be 3L divided by R, assuming 0 propagation delay. So here we are assuming that the propagation delay is 0. So we are accumulating the total delay with this formula. Okay, we will study delay in more detail shortly. Okay, for example, you have a file of size 7.5 megabits is the size of the file, and the data rate is 1.5 megabits per second. In 1 second it can transmit 1.5 megabits, and the transmission delay in this case will be, because 3 into 7.5 megabits per second divided by 1 megabits file size divided by 1.5 is the data rate. It will take approximately 15 seconds to transmit a file of this size. What are the comparison? If we have a comparison between packet switching versus circuit switching, which technique we should say that is more better as compared to the other one in terms of accommodating more number of users? So packet switching allows more users to utilize the network or to use the network. For example, if we have 1 megabits per second link, 1 megabits per second, the capacity or the data rate of the link is 1 megabits per second, and each user is getting 100 kbps per second when it is active. It's mean how many users are sharing this link? 10 users are sharing this link if we go for circuit switching. Okay, 1000 bits per second is the data rate divided on 10 number of users. Each user will be getting 100 kilobits per second when it is active. It's mean 10% of the time the link will be kept active if one user is sending a data on the link. But if 10 users are sending data on the link at the same time, it's mean it is utilized, it is kept active 100%. Okay, so in contrast, if we look into packet switching technique with 35 users, the probability will be more than 10 active users at the same time is less than 0.0004. How did we get this value? How you can have this probability of with 35 users that the probability is greater than 10 active users at the same time is less than 0.0004. This is your homework problem number 6 in your textbook. So you have to solve this problem and come up with an answer. Okay. Packet switching versus circuit switching technique. Is packet switching a winner technology or technique over the internet? You could say that it is great or good technique for busty data, for huge data if we want to transmit it over to the network. Why? Because as we said that on the internet we are sharing the resources. It is simpler and it does not require a call setup. Okay. Whereas there are more chances of congestion over the network and packets could delay, and there are chances that the packets will be lost on this on the internet when we are using packet switching technique over it. So we have to take care of congestion, delay, packet losses. Okay, we will look into these issues and we will study the layering model in detail. Protocols needed for reliable data transfer. We do need protocols in order to control all these things, in order to control the congestion over the network, in order to give reliable data transfer. Okay. How to provide circuit like behavior if we do need some guaranteed data rate, guaranteed bandwidth over the packet switch network. For example, on the internet, if you do need the properties of a circuit switch network, so what is the solution? Bandwidth guarantees needed. For example, for some applications you do need guaranteed bandwidth. For example, for audio and video application you can't afford delay. As on the telephone network, at the same time you are talking, the other party is hearing your voice. But if a congestion comes on the internet packet switch network, is it affordable? Definitely congestion will lead towards the delay. So if there is a delay on the packet switch network on the internet, can you afford delay? For the voice applications or for the video applications, having a jerky video, start and stop, start and stop, you can't afford it. So it is still an unsolved problem. We'll have a detail on this in chapter number 7, but scientists and researchers and the people who are working in this area, they are continuously trying to improve and trying to develop new techniques to cope with these problems, and continuously improving the protocols and the ways to give better performance, optimal performance, trying to achieve up to the optimal level with the packet switch network. Let's have a look into the internet structure. What is the definition of the internet? As we discussed in the first lecture, it is a network of networks, combination of so many networks or a lot of networks. For example, LANs, if you connect them together with the help of MAN or WAN, it will be converted into a biggest network, which is called the internet. We can call that internet is roughly hierarchical. At center, you will have the tier 1 ISPs, example Verizon, Sprint, AT&T, cable and wireless, to give national and international coverage, treat each other as equal. And they will be connected with one another. So tier 1 providers interconnect privately. For example, if we take this snapshot, tier 1 ISP example is Sprint. So all the tier 1 ISPs are connected with one another, okay, with their own private links. So they should have their point of presence. So these are their point of presence, and they can have a peering connection with the other one. For example, this one, this one, this one. Two from the backbone. This is two from the backbone. This is two from the customer. And this is the peering between them. Tier 1 will be serving the smaller ISPs, often the regional ISPs, and those ISPs will be called the tier 2 ISPs. Connect to one or more tier 1 ISPs, possibly other tier 2 ISP. So they can be connected, they can be served by the tier 1 ISPs, and if they want to connect, they can connect again privately with their equivalent peer tier 2 ISP. And one tier 2 ISP can be served by more than one tier 1 ISP. Tier 2 ISP pays tier 1 ISP for connectivity to rest of the internet, because tier 2 can get the internet service from the tier 1. So for that service they have to pay to tier 1. Tier 2 ISP is customer of a tier 1 service provider. Tier 2 ISP also peer privately with each other. So two tier 2 ISPs can have a private connection with each other. Then it comes to tier 3 ISP and local ISPs. They can get services from the tier 2 ISPs, last hope access network, and they are closest to the end system. So tier 3 can get from tier 2, or local ISPs can also get services from tier 2 ISPs, and then further local ISPs can give or can serve the local hosts. Yes.
Do you have an example of tier 2, tier 3?
Yeah, you can say tier 1 here in Saudi is STC. Okay. Tier 2 you could say it is Mobile. Okay, because they are getting the service from the national carrier. Who is the national carrier? STC. Tier 1 STC, Tier 2 Mobile, and then if a local ISP is working here, they can get service from Tier 2, for example, from Mobile, and they can serve in a building, number of homes, for example, privately. Okay, or otherwise here, as the structure here in Saudi is, Tier 1, even Tier 2, they can serve directly to the last hope users. Okay. Local and Tier 3 ISPs are customer of higher tier ISP, connecting them to the rest of the internet. Okay, so they will be served the last hope or the access on the access network, the last hope, the hosts will be served by the local ISPs or the Tier 3 ISPs. Now, if a source host, wants to send a packet to a destination host, it will pass on through many networks, isn't it? If this host has got an ISP connection or service from the local ISP, so from this source host it will go to local ISP, from local ISP to Tier 3 ISP, from Tier 3 to Tier 2, from Tier 2 to Tier 1, and then it will be routed wherever it has to go, because all the Tier 1, they are connected with the internet backbone. The internet backbone is landing over here on the Tier 1 ISP location. For example, look here how the packet from this source host is traveling through how many networks and reaching to the destination. Local ISP to Tier 3 to Tier 2, Tier 1 to Tier 1, Tier 1 to Tier 2, Tier 2 to local ISP, and then to the final destination. This is the structure of the internet, which is a network of networks, and how a packet passes through many networks in order to reach till the destination. Clear? So we will stop here, and in the next lecture we will start with delay, loss, throughput in packet switched network. Thank you.